Hey, what's up, guys? This is Chung here again. So this time, 1932 merge BSTs to create single BST. Uh, this one, I don't know what to say. It's kind of annoying. So this one is kind of long, and it's kind of straightforward, but the implementation is kind of tedious. So basically, you're given like n BST binary search tree root node for n separate BSTs stored in a array in a tree arrays, right? And each BST has at most 3 nodes. Okay, and no two roots have the same value in one have the same value. And in one operation, we can do this thing. Basically, we can merge two BST by doing what? So we need to select two BST where one of the BSTs, the leaf node, the value is the same as the root of the other BFT, the BFT, sorry, BST. And then we concatenate, right? We concatenate that root to the leaf node, right? And then we remove that from the trees, okay? And our goal is to try to merge all the BST trees into a single one, right? And then within n-1 operations, obviously. If it's impossible to merge, right? So you all know what the BST is, right? So here are some examples. So for this one, we have 3 BST tree, and the answer is yes, because we can merge it. So the answer, so first, right? So first we have two options here. 2 is the same as this 2, right? That's why we can replace. Basically, we can concatenate. We can merge this 2 in here, right? And it is okay because once that is done, this one, the 2 only has the one here. After merging it, it's still a valid BST tree. BST, right? And then second time, right, we're gonna merge this one with this one, right? So now we have 5 and 5, right? That's why this one, after this one, this one is also like a valid one, right? That's why the answer is true, which means we will return this the merged BST. And the second one is false. It's not false. It's like empty. It means that okay, so even though we have 3 and 3, right? But as you guys can see, once we merge this one is not a valid one because 2 is fine, right? This one is fine, but 6 is not, because 6 is greater than 5. That's why we cannot merge it, and that's why the answer is empty. And example 3 is also another one. The answer is obviously empty because there's nothing to merge, right? And then the example 4 is the answer is yes because it's already a BST. Cool. And there are like some constraints. Okay. So, I mean, to solve this problem, I spent a lot of time trying to rule out all the invalid scenarios, and I think the first one is that we have multiple. Okay, I think the first one is that how can we find the root of the new BST, right? So what's gonna be the root basically? Um, after drawing some of the examples, I think the root, one of the observations we need to make here, the root the root should not appear at any of the leaves node of all the BST trees, the BST. And why is that? Um, let's say we have a root 1, right? And then we have this one, and we have this one, and then we have some root 2, right? This is also like another one, and root 3, right? So if it exists like a merged BST in the end, so the root of the merged BST tree, the BST cannot be any of this leaf node. And the reason is that, let's say we have 6, 2, and 8, right? And then we have another one is like what? Let's say 10, 6, right? And then 12. Okay, how about this, right? I'm saying that, the 6 will never be, can never be this the root node. And why is that? This is because, if we use 6 as a root node of the merged BST tree, so this one eventually, this one will merge somewhere below this root, either to the left or to the right, right? But since we have a same value here, right, that means that, this one will definitely not gonna be a BST, because the BST, any node on the left side should be strictly smaller than 6, and any node on the right side should be strict greater than 6. But we already have, like, since this subtree will eventually be merged somewhere down below, but we already have like a node which is the same as the root, then this is definitely not gonna be a valid BST, right? So that's why the first observation is that, basically we need to have, so basically the merged root has to be, should not exist in this in any of the leaf. So we need to find that root first. Okay, but what if we have two roots, right? That doesn't exist in any of the leaves, right? I mean, if that's the case, I mean, those two will never be merged, right? It means that, we will never get like a BST tree in the end. So we can just simply ignore, handle that one along the line later on. Because, so basically, first step, what I did was I tried to find the merged BST root node by finding out the first root that does not exist in any of the leaf nodes. Okay, and after that, right? After that, once we have the root node, we'll have like two leaf nodes that we can merge, right? And from there onwards, basically, I'm having a while loop here. I'll have a while loop, right? And then within the while loop, I'm also maintaining like current leaf node, current leaves. Basically, these current leaves will be the leaves on the current merged tree, and I'll simply loop through these current leaves, try to find the next one if I can merge, right? Until I have merged everything together. So that's the basic idea. And okay, and then the next thing is that, when we try to merge, right, we need to check if we can merge the current tree to the current node. Oh, and another one is this. And while we're merging this, the BST, whenever we have find two leaves which have the same values, we can simply just stop and return none. So what does it mean? It means that, while along the line here, right, where basically this is a root, right? We merge this one, and then we merge this one, and then the next time, okay, we can merge this one and this one, right? So let's say at this moment, there are two leaf nodes. So we have 4 here. 2 of them have the same value, 3, 3. Obviously, this is gonna be an invalid case, right? It doesn't really matter which they are. I mean, as long as there are 2 leaves node has the same values, we simply return null, because this is definitely not a valid one, because each of them should have different value, right? Because otherwise it will break the BST. Okay, so that's the another thing. Oops. And the last one is that when we try to merge, right? So let's say we have this tree here. Okay. So let's say we try to merge this one. Let's say we have 8, and then uh, 2 maybe. Okay. Here we have, let's say we have 4 here. Okay. And then this is 1. Doesn't really matter this part. Let's say if we're trying every time when we try to merge, like if we find out, okay, there's like another subtree BST with a root of 4, right, with some left and right, so left and right. So how can we know if we can merge this 4 to here, right? So as you guys can see, we need to check, right? We need to check. Okay, so basically each of the BST is a valid one that we don't need to worry. But what we need to check is that if this left and right are within the range of what? 2 to 8 in this case, right? Because as you guys can see, this 4 is within the range between 2 and 8, right? Similarly for this one is like what, to negative this infinity to 2, right? And how about this node? This node is like what? It's 1. Sorry. Oh, sorry. This leaf node is not. It's not like it's not a leaf node. So what I'm trying to say is that what I did was for each of the leaf node, for each of the new leaf node I did, I'm also maintaining the range for this leaf node. Basically, for this one it's going to be 2 to 8. For this one, it's going to be a negative infinity to 2, right? And then since we have that, right, and when we try to merge it, right, we simply can check if both the left and right are within the range of this leaf node. If it is, then we can merge it. Otherwise, we don't, right? Otherwise, we can't merge that. And if we cannot merge that, and then we simply return none, right? Because if this one is not valid, it means that we'll never be able to. And since we cannot have two nodes have the same values, and which means this is the only chance that this subtree can be merged. But if this one doesn't work, then we know we cannot build the BST. We can simply return none at that moment, right? Cool. So I think that's pretty much everything I want to talk about. Oh, and another one is this. Okay, the last thing, since we need to return the final the merge tree, right? So and then so after merging this tree here, right, we also need to basically to update the left and right pointer. I think for me, what I did was that, while I'm having that current leaves node, I'm also saving the parent node along with it, so that I can just I can I can restructure the tree when the merge is feasible. Okay, that's why I think looking at my implementation, it's kind of long, so I don't know. I don't have time to refactor it, and that's what I'm doing. What I did, and just take my code with a grain of salt. I know it's kind of tedious and long. Okay. Let's see. Where do we start? So first step, right? Find the root. Okay. So we have leaves gonna be set. Okay. So first I try to find all the roots. So that's when I need to find all the leaves in the tree, right? So if the tree has left, right, and then I do a leaves dot add, right? Tree dot left dot value. Okay. If tree dot right, I do if tree add this one to that. Okay. That's how I find all the leaves. And then for the root, right? So at the beginning it's going to be none. So I do another for tree in trees. Okay. If tree dot value are not in the leaves. Okay. And then I do a root equals to the tree. That's the real root, right? And then I break. Okay. And if not the root, return none, right? Because if we cannot find a root, we obviously we need to return none. Okay. And okay, so once we have the root node, right, and then we can have the leaves, right, the current leaves that we can are the candidates with that which we can use to merge with other BST. Okay. If root dot left, right? So if I have that, we do a current leaves. So the value is going to be root dot left dot value, right? Sorry, the key is that, and the value is what? The value is like the first one is the range, right? So we have the lower range, which is system dot max size negative, and to the root dot value, and I have a root, and I also have like so the last one is this basically. This is what the lower bound, the low bound, the higher bound, and then the I think it's kind of hard to see it, right? Since this is too wide. Let me change this one to this one. Okay, yeah, I think this one is much better. And then we have the parent, right? So we have the parent node, and then left or right. I know I'm saving a lot of things here, you know. Basically, I need this one so that I know when we try to replace it, we need to know if we want to replace the left one or the right one. Okay, so 0 means left, 1 means right. Okay, and then for the right one, I can simply copy and paste. Right. So if we have another one, have a right. So this one is going to be the from root dot value to this one, system max, right? And then the root is 1 and root and 1. So that's the starting point of the current leaves. Okay. And then while what? So while there's still some trees that hasn't been merged, right? So this is the list. Can we use this one? The trees is like a list, if we try to remove that, it's going to be O of n time complexity. Let me create like a tree dictionary, right? So basically I'm just converting these trees into a tree dictionary so that I can have like O1 time of remove, right? Because here, I'm going to do something like this, while this tree is not empty, I'll try to merge, right? And every time when I find a merge, I'll delete. I'll delete the tree from this dictionary until this one is empty. That's when I stop, right? So here, I'll just use this for loop to do it. So basically, tree dictionary dot tree dot value gonna be the tree, right? Yeah. Cool. So now we have this while loop here. Let me see. So find. I have a flag here. Basically, whenever we stop, right? if we find like 2 leaves, basically if we cannot find like a next tree to merge, right, and then we'll stop. Basically that's why I have a find tree, gonna be the false, right? And then for leaf, and then we have a low, high, parent. Basically, I'm trying to find a loop through everything in the current leaves. Okay, items. Right, I try to find if there's any leaves that can be used as a next candidate to merge with another BST, right? Left or right. Okay. So this is a leaf. So first we check if the leaf is in the tree dictionary, right? Because we have so many leaves here. This leaf may not have a root, right? As in the may not be a root node in this remaining tree dictionary, right? That's why we need to do the if check here. And if it is, and then we have a new tree, gonna be the tree dictionary of leaf, right? Okay. And okay, and then we find that, right? So then we can so here I delete the leaf from the current leaves node. Okay. Then I check if this new tree can be merged or not, right? So like I said, we need to check both of the 2 nodes are within the range of this low and high, right? So if the new tree dot left is not empty, then I check if the new tree if the low, right, smaller than the new tree dot left dot value, right, between the high, right? And actually I'm also checking another one. Basically I'm also checking if there's no duplicated leaf node at this moment. Basically if the new tree dot left dot value are not in the current leaves, right? So I check 2 things. The first is if this one is in the can be within the range. The second one is that we don't allow any duplicated leaves node at any moment, right? So if that's the case, uh, we can add this one. It means that okay, at least this we will have like a new leaves candidate, right? So it's gonna be a left dot value, right? So because we're adding this one, once we merge this tree, we'll have like a new leaf node, right? With a new range. So it's gonna be a low since it's a left one, right? To the new tree dot value and the new tree and 0, right? Else we simply return null, right? So similarly for the right one, right? So for the right one, I can just do the same thing here. It's going to be the right, 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 and but here, right? So here we're gonna have like a new value to the high, right? And then here's gonna be instead of 0, we have 1 because this is the right node, right? And cool. So now we have merged this current tree, right? So now let's update parent node. Okay. So if the left or right equals to 0, I do this. So parent dot left gonna be the new tree, right? Else parent dot right equals to new tree, right? Okay, cool. And then okay, so at this moment, okay, we find a new tree to merge. So then we set this find tree equals to true. Okay, and then the last thing is that I delete this one. I delete the new tree from the tree dictionary. New tree dot value, and I break, right? So outside the for loop here, right? The if not find tree, right? So if we didn't find a tree to merge at this moment, we return null. Okay, right? Else, when this while loop is finished, it means that all the trees have already been merged, right? Because we delete trees from it. Oh, that's when we need to return the root, right? When this one is empty. Oh, I think we forgot one thing here. Basically, we have to, before running the for loop, the while loop, we need to delete the root node from the tree dictionary. Since we're using this tree, we're checking if this one is not empty or not, right? So we have to delete this root dot value from it. Okay, cool. And I think that's it, maybe. Yeah. So if I run the code, all right, accept it. Right, just submit. All right, cool. It passed at least, right? Even though it's not that fast, still faster than 100%. I'm not sure where did that number come from. Yeah, I know. See, so this one is a pretty long implementation with a lot of intermediate state, right? I store these 4 values for each of the leaf node. And then along the way, I also check if there's any duplicated nodes here, right? I believe while we're doing this for loop here, we can also check if if there's any duplicate nodes in this leaf set at the very beginning. But I didn't do it. Seems like it didn't break any test case. It seems like we already guaranteeing everything here, so that we don't have to check if there's any duplicated leaves at right here. But I think checking that won't hurt anything, right? Yeah, as you guys can see, this is a pretty long implementation. I think it's mostly because my implementation is so bad and tedious. And about time complexity, honestly, I don't quite sure about time complexity. Maybe if everything works fine, right? If everything works fine, even though we have for a while here and we have for loop here, I mean, it seems like I have a feeling it's gonna be a O of n in my case, because if everything works fine, we should have like find a leaves very easily, right? Shouldn't loop through too many of these things here. So that's why I think overall should be a O of n time complexity if I didn't miss anything. Yeah, I think that's it, right? I mean, this one, I think the trickiest part is that we have to be able to find the root, right? So which means we have to know the root should not be the same value as any of the leaf node. And once we have the root, I think the rest is just like trying to merge, right? Trying to maintain like a leaf node and trying to merge it along the way, right? And then we have to maintain some of the values for each leaf node so that we can check the validity of the next new BST to merge, right? By checking the range, the lower and higher range, and then also the parent and this thing to make sure we can modify the tree properly, right? And yeah, I think that's it for this problem. And thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.